that visible? Yeah. Okay, that distance down there. Yeah. I don't think that shows on the actual video, but yeah. Okay. So we defined what our variables are, and we know what depends on what. If you go, when you first get in that cab, how far have you gone? 0. How much does it cost you? $2. Okay, so you can mark that on the graph. What's our starting point on this quadrant? Yeah, 0. 0 for x, 0 distance, but it costs you $2. Okay. Now, after 1 mile, how much do you owe the cabbie? $5. Right. Why 5?
Oh, well, the flat fee.
Yeah. The $2 flat fee plus $1, $2, $3 more for the 1 mile. Okay. So after 2 miles, how much do you owe him? Right. 2 times 3. 2 miles times $3 each, $6 plus your $2 flat fee. Now you can keep making these mental calculations. Let's make a little quick T-chart, not to be too tedious with it, but you know from 0, when you first get in, you owe them $2. Okay. How about when you owe him, when you've gone 3 miles? Right? 3 times 3 miles each is 9 plus 2 more. What about when you've gone 8 miles? Right. 8 times 3, 24, plus your $2 flat fee. Now, go ahead and put those points on here. We got 3 and 11, and 8 miles, $26. And you can see, of course, that linear relationship. And we're expecting that because his rate was constant. Doesn't change depending on how many miles you go. With that constant rate of $3 per mile, that is our slope. Rate of change is slope. You can see that no matter where you are on this line that demonstrates how much you owe the cabbie. That line isn't bending or curving. It has that constant slope, that constant steepness, which is that because of that constant rate. So to avoid having to keep doing this, how much do I owe this? Let's write a function that we can use to determine any amount of mileage we want to go, how much it's going to cost us. Okay. So if we start off with y, because y, the cost, depends on what factors? Right. So we've got a per rate. Now that per means multiplication. $3 per mile. And since x is our miles, $3 times that. Plus that flat fee that is not, if the flat fee is not affected by a variable, it doesn't change. No matter how far you go, 1 mile or 100, you got to pay that $2. Okay. And then, of course, in function notation, because this is also the same thing as f of x, we could write it as f of x equals 3x plus 2. Same thing. Okay. Now, as pointed out, what is the slope of this line that it creates? Okay. And what is that number? 3. Right. Okay, so there's a slope. The slope is 3, or 3 over 1. If you're going to graph it, you need that ratio, right? Okay. And this is literally the rate of change. Okay. How much what you owe him goes up, and it is a constant rate of change. So having that formula and having that function now, you can answer a variety of questions depending on what you're given. For example, if you were asked how much would it cost to go 20 miles? Okay. Remember, you have to, just like in the problems we did before, you're asked questions about a function. Well, there's 2 variables, and in order to answer a question about that function, you have to be given one thing, because you can only solve an equation for one variable. So you have to be given one and know which one is missing. So in this question, which one is given? X. Yeah, the miles, so that's your X. And what's unknown is the value of the function.
4.
And so f of 20, you want to find out how much is it going to cost, the value of the function, the cost, when x is 20. So 3 times 20 plus 2. So for 20 miles, you are going to owe. Sorry? The 20? Oh, just because that's the question I asked? Yeah. So if I ask this question, given what we know about this cab and the function we just wrote to tell us the cost, how much is it going to cost to go 20 miles? Well, given 20, if I tell you 20 miles, you say, okay, well, that's my x. And the value of the function, I'm going to plug in x for 20. And the value of the function is how much it's going to cost me once I simplify. Make sense? All right. On the other hand, you might say, if you have $30. Okay? So you want to get home, but you only have $30 in your pocket. Well, plus a couple extra dollars you stuck away for tips, because you don't want to stiff the cabbie on that. But you got $30, and you tell them, look, I've only got 30. Besides your tip, I've got $30 to take me as far as you can go, and I'll have to walk the rest of the way home. Okay? So you've got $30 to pay them. So how close can you get to home? How far can he take you? How far can you go? Can you go? Okay. So again, you need to have an x and an f of x. Which one do you know? Yeah. You know which, sorry? F of x, right. You know the value of the function, the f of x or the y. Okay. How far is right there. How far is the unknown? That's your mileage. That's what you don't know. Okay. So your f of x is 30. So you just take your function, plug in 30, because you know that. You got $30 to spend. And so how far can you go with that $30? Now in this case, because you know how much the value of the function is, solving for miles means you actually have to solve for x. Which is not a problem. It's a single variable equation, because the other variable you have the information to plug in. So minus 2 on both sides. Divide both sides by 3. Which is, yes, approximately equal to 9.3. Even though, like when I'm just having you solve a graph equations, stick with fractions and lowest terms, real world problems, decimals are often more appropriate. So you can go about 9.3 miles before he says, okay, you're done, you got to walk the rest of the way. Okay, so 9.3 miles. I always use units for the thing that's missing. Make sense? Okay. All right. So how about this relationship? I'd like you to think about this. What I'm going to do is I'm going to put increments on the graph, but I'm not going to label the axes. So I want you to decide what are your x and y's. How would you label the axes? Okay. And how would you write the function that goes with this? Okay. So you've got a new car on the lot, okay, and it costs. Say this costs $15,000. And what happens once you drive a new car off the lot?
The value goes down.
Right. So you're going to have, that car is going to depreciate. Its value goes down each year. It depreciates. Oh, yes. There we go. Yep. It depreciates $1,500. So decide your x and your y. What depends on what? Actually, I'm not going to label the increments yet because that'll give a clue, so I'll take a second there. What depends on what? You've got two variables thing. Here are two things that change, and one changes because of the other. So these married together as ordered pairs, and x changes a y. So what is your x and what is your y? So what is it that changes? The value of the car, right. And what does that change depend on? Exactly. So X, our independent variable, is time, specifically in years. And Y, the dependent variable, is that value of the car. It's like, what is this car worth? Well, it depends. How many years have you owned it? So our x-axis is time in this case. There's a distance up here, time here. And our y is value, also a money thing, specifically value. You're not necessarily selling it, but what is its value? And let's go ahead and label the increments. That, of course, is 0, 0. And let's label the value by 1,000. So I'll make that 1,000. You have to label every one. I'll do it by 5,000 sounds. So 1,000, 2, 3, 4, 5,000, 6, 7, 8, 9, 10,000, 11, 12, 13, 14, 15, 15,000. Okay. And let's label time by years, increments of 1, 2, 3. So we're going to figure out when you first buy that car, year, time 0, after 1 year, after 2 years, after 7 years. Okay. By the time you get to 7, that should get a little tedious. Go ahead and write the function that goes with that. Do the first two sort of couple mentally so you can start to sketch in your graph, and then that will also help you then write because there's something specific about this, how this function is going to look. I want you to notice. Where's your paper? Did you write it?
Yeah.
At time 0, what is y? And after 1 year, what's the value of the car? Right. 13,500? Right. That's a little bigger numbers than working with the cabbie. So after a couple of years, I need a formula, to be able to just plug into. So after 2 years, how much value has been lost on the car? 3,000, right. So it's the value of the car after 2 years is? I'll go ahead and put those on here. Now, is the value of the car, is it depreciating at a constant rate, or does its depreciation change every year? Constant. Yeah, every year you can count on. And in the real world, it's going to actually make more of a curve because, after time, it's never going to be worth 0. Okay? You're always going to get some parts for it or something, probably. But, but just as illustrative purpose, right now it's a linear relationship. It might curve off in the real world towards the end, but for right now, you're seeing that constant change. You can expect $1,500 a year comes off the value every year, at least for now, for the foreseeable future. It's a linear relationship. But how does it differ from the one of the cab? Right. So let's put a couple more values and we'll connect that dot. But let's work with a function now so it's a little easier to manipulate. So we've got our function. Let's just start with y, the value of the car, because that's the dependent variable. The value of the car depends on what's changing. Huh? Yeah, the year changes, and what happens each year? Yeah. Right. So what is our rate of change?
1,500.
Right. Yeah. So is x, what's happening between the x and the minus 1,500?
Yeah.
multiplied, right, it's still a rate of change, right? Just like up here, the rate of change is $3 per mile. This rate of change is $1,500 per year. Okay? So if we had $3 per mile and miles were X, then that's 3X. 3 per mile is 3X. Okay? This is $1,500 per year. X is years. So $1,500 per year, you write that down, per year, gives us what as our first term? Right. Now that $1,500 is negative instead of positive because we're losing $1,500 per year. Now we're not subtracting. I mean, yes, that's what we did. We're doing mentally. We're subtracting $1,500 per year. But if we're going to put it in this formula, that per year says, well, we can multiply what year it is times negative $1,500, and that's going to give us what kind of number? Positive or negative? Negative. Yeah, because year is always going to be positive. Times negative $1,500, you get a negative number, and then the rest of the function is right. There's the initial value, but you add a negative number, right? Negative $1,500 after 1 year, negative $3,000 after the second year, negative $4,500 after the third year, and so forth. You end up with a $15,000 that goes down, 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 down. But this is the rate of change per year. And per is that multiplication right there. Written as a function, of course, be f of x equals negative 15x plus 15,000. And still we have that m equals negative 1,500. Because it's negative, we know it is a line of depreciation. It's a line of value is decreasing. That downward sloping line. But it is, in this example, a constant rate. It's always $1,500 per year, which makes that linear rate, that linear or constant change. So if I wanted to do 7, for example, and I want to know the value of the car after 7 years is, I'm going to lose $1,500, lose minus $1,500 per year. And that's going to be a negative number that will be taken from my original value, which is, all right, $4,500 once you plug that in. Now, of course, at this point you could say, well, okay, so that's after these certain years. I can say, well, what year, what will the value of the car be? And you can also go in the other direction. You can say, you know what, before this car goes below $6,000 in value, I want to sell it. Okay, so how many years can I own this car before I want to sell it, before it goes under $6,000 in value?
4, 5.
Yeah. Now, we could plug in 6,000 for f of x and figure out what year that is. Or we can also see it visually now too. Is that what you were looking at here? Yeah, so I know 6,000. Here's 6,000. So if I move over, I can visually see, okay, right now while I'm at 6,000 value, time up here, I'm good. The value is above 6,000. But as time passes, the value of the car is getting closer and closer and closer to 6,000. Okay. So yeah, around 5, probably about year 5, I want to sell it. Because by year 6, I've fallen below the value that I want to make back from the car. So you can plug that into the right place in the formula, and you can also use your x and y on your graph to visually see when things are above or below a certain level. Okay. So to sum up from these two, that linear relationship has a constant rate of change. And that rate of change might be increasing if it's a positive slope, like from above, or decreasing if it's a negative slope, like in the second example. But either way, it's always the same rate, okay? And that is what your slope means. Okay. Now, if you've got something, and when you've got different increments on some of these real-world problems, when you've got different increments, it can be harder to see this part, okay? But if you think about it, if you've got something, if you've got an upward relationship, so something is increasing and it's a really steep line, then is it increasing, is your rate increasing really fast or really slow? No. And if it's a really shallow line, then change is happening, but it's happening pretty slow. If it's a downward line, it's the same thing. If it's a steep downward line, then the rate of change is things are moving really fast. Okay? Like, for example, the car is depreciating. Some cars depreciate really quickly. They lose their value really quickly. And others hold their value for a long time, and their depreciation line will be much shallower. Because they keep their value. Maybe they're better made, or they have a better reputation, and their value stays higher for longer. So you can put two graphs on the same graph and compare, how to, over time, is it better to spend more on a car that's going to depreciate more slowly, or spend less on a car that's going to depreciate more quickly? At what point do those lines cross? And you're like, well, which would be a better deal? Kind of depends on how long I plan to keep it. And you can also, those are systems of equations you can compare as well. Okay. Comfortable with this? Okay. We're going to have to tackle some of those word problems that you'll see in the homework as well, and you can expect one or two of these on the exam as well. Okay. So this will be, I'm going to scan this in with that function handout as well too, so you can go back and review if you missed anything on it. Okay, so. Okay. All right. All right, so let's focus in a little more specifically on slope and ways we find it, and end up with we're going to end up working with specifically horizontal and vertical lines, and also hopefully a little more graphing practice if we have time. Just a reminder, depending on how much time we have here, but this was the handout that I handed out here, and there's a copy of it posted on my math lab as well. And this gives you that whole breakdown in what a linear function is, the different pretty forms it can be written in, all the characteristics of that form, and the steps for graphing it, and some graphing practice. And it does that for whether it's in this pretty form, function notation or slope-intercept, standard form, ax plus by equals c, and also horizontal and vertical lines. Okay? And so we're going to end up today looking closer at horizontal and vertical lines and do some graphing practice if we have time. Remember, I'm going to fill these in and scan this as well, so if you can do the graphing practice here. If you can hand graph the lines that are in this handout without a problem, you're good for the exam. If you have any problems with these, you want to send me an email and work with me, or come down to the lab, or ask questions on Thursday. Okay. So slope, as we've defined as rate of change, and specifically visually is the steepness of a line. And there's multiple ways to find slope. It depends on what you're given. So if I ask you to find the slope of something, your first thought should be, well, what information am I given? Okay? So actually first, let's look at one way to find slope is on a graph. Okay? So let's look on the back actually of this. We got a graph with some. I want to do that. Yeah, that's what I want. Okay. Actually, you have to flip it upside down, actually, there. The way I Xeroxed it upside down, actually. Okay. Okay, so one way to find slope is to count it off on a graph, and this is going to lead to what we do on Thursday as well as writing equations. So you can count it off a graph. Okay? And the important thing to remember is that you are looking for rise over run. Okay? The order you count it off matters. Okay? You think of it like a stair step, and it doesn't matter what direction you go in, if you're going from left to right or right to left, but you always go up or down first. Algebraically, you can write this as change in y over change in x. That little delta means change. And that just means subtraction, or change or subtraction, and that is when you're counting off, the top number is always up. If you have to move up to get to the second point, or down, would make it either a positive or a negative value. And then to get to that second point, you move over either right, which would give you a positive value, or left, which gives you a negative value. So if we look at this line, for example, here's 2 points marked on it. So to move from, I think I'll move from left to right, so that you can also count it right to left. Now I see visually that this is a downward line. So what kind of slope am I expecting? Positive or negative? Negative. So it's always a good idea to look at a line and see, what are my expectations? Okay? Or if you're about to graph a line, look at the equation and think, what are my expectations? And make sure these are little checks as you go. Did it meet my expectations? Oh, no, I'm at a careless. I still do this when I graph a line. Like a lot of times I'll be like, wait, that line should not be downward. I was expecting an upward line. And I fix it because I just sort of reversed my negative. Okay? So the important thing is to find those little things and catch them as you go. So expecting a negative slope, I'm going to start from this point, and I want to get to this point. So to get there, I'm going to do a stair step to get to from this point to this point. First, I have to go up, down, left, or right. I'll either have to go down or right. Which one should I do? Right. Down first. Remember, the top value, the first thing you're always doing is up or down. And so I'm going to go down how many units? Right. 1, 2, 3, 4, 5 actually, yeah. So I've got 5 units down to get level with this point. So is that positive 5 or negative 5? Negative. Right, because it's down. And then to get over all the way to that point, I go how many units? And is it positive or negative? No, positive. So I went 5 down, which is negative 5, and 3 to the right, which is positive 3. Now if I'd gone from right to left, I would have gone up 5, positive 5, and 3 to the left, negative 3. Is that going to give me the same slope? If my slope, as I counted it, was down 5 over 3 to the right, is that the same thing as if I had gone up 5 and then 3 to the left? Yes. Yeah. Yeah, so it doesn't matter whether you count left to right or right to left. It doesn't matter which is the first point and which is the second point. It doesn't matter if I use this point and another point on the line. The slope is constant on a line, and you will always have the same slope. So in this case, the slope, and because it's negative, if one is negative, the whole thing is negative. I just pull that negative out front, so it's negative 5/3. Now, am I expecting a positive or a negative slope? Is it going to be a very high number, greater than 1 or less than 1? Yeah, because that's a pretty shallow line, a very slow rate of change there. This slope, is it greater than 1, or the absolute value I'm talking about? Is the absolute value of the slope greater than 1 or less than 1? Greater, because it's an improper fraction. And that's a pretty steep line, huh? Not super steep, but definitely greater than 1, greater than average. Okay. So I was expecting, looking at this line, it'd be negative and probably greater than 1, because it looks a little on the steep side. Here I'm expecting negative, but less than 1, because that looks pretty shallow. Okay. So if I move, it doesn't matter if I'm here. I'll move from right to left, just to be. It doesn't matter. One point to the next. To get from this point to this point, first I have to go up. How many units? Positive or negative? Right. And then to get to my second point, I have to go back this way. How many units? Positive or negative? Yeah. Right. So 1 up, 6 to the left. Or I could have gone 1 down, negative 1, 6 to the right, positive 6. Either way, you get a slope of, now one's positive and one's negative, so I can just put that negative out front.